So you saw that it's pretty straightforward to perform alternate logic gate representation. You do two things. First, you change the shape, and then you change anything uninverted to inverted and anything inverted to uninverted. So that's how you do it. But why would you want to do it? Well, you do it to make a circuit sort of respond how you want it to respond. You also do it because you should design a circuit so that the inverted outputs are connected to inverted inputs and non-inverted outputs are connected to non-inverted inputs. So here we have a problem. So the problem is this is inverted, but this is not inverted. So you should avoid circuits that are designed that way. So that's one of the reasons we do that. We also do it to make a circuit perform a certain way. So this is my original circuit here, and it's not ideal in its design in that we have some inverted outputs going into another input. So how do we want to redesign this? We can do this two different ways, and it'll be the same circuit performing in different manners. So let's say it depends on what happens, out here. Do I want to, I'm activating something out here. So here's some equipment or some machinery in this green box. And do I want to activate that machinery with a high signal, makes it go? Or do I want to activate it with a low signal, makes it go? So that's my question. So first of all, I'm going to draw it where I want it to activate the rest of the system when something turns high. So I want Z coming out to go high, to turn into a 1. So I'm going to do an alternate logic gate representation so that where Z is not going to come out with this active low here, it's going to come out with an active high. So I don't want the output Z to be inverted there. So I'm going to look for an alternate logic gate representation of this. Well, if I were to do the alternate logic gate representation of that, I would change its shape. So it has an AND shape. I'm going to change it to an OR shape. And I had two inputs that were not inverted, and now I'm going to invert them to get the alternate. And the output was inverted, so I'm going to leave it not inverted. So this is what is called active high. Output. So that active high is going to be connected to the rest of the circuit. And now it's preferable to have this inverted outputs coming out here. So I'm going to, that's so that these match. That's so that this matches and this matches. So I'm going to leave those NAND gates as is. So this is my alternate logic circuit that performs like the original, but it performs with an active high output. So I wanted to change this original circuit into one that has an active high output. I also wanted to match the inputs and outputs. So here, Z is going to go high. Z is going to equal 1 if X, I'll call this X, I'll call this Y, are low. So if X is low or Y is low, then Z is going to go high. And in order to get X low or Y low, then A and B must be high. That's this line in the truth table for a NAND gate. Or C and D must be high in order to get a 0 here, or here. And that's how that circuit works. So therefore, in order to get the Z out the back of the circuit, um, A and B or C and D must be input values of 1. That's how this version of the original circuit works. Now, what if you want to activate that rest of the equipment, that green box that you're making go? What if you want to make it go with a low signal, with a 0? Well, then that's called active low. I'm going to take away that circuit, but I want active low here. Well, the original circuit was already active low. So I'm going to keep that NAND gate. That's an active low original circuit. But we notice that we have the inputs to this NAND gate are not inverted. So we should have the outputs of the previous gates not inverted as well. So I want to get rid of these inverted outputs. And in order to do that, I can take the alternate logic representation. Oops. I can take the alternate logic representation of this and this. In order to take the alternate logic representation, I want to change the shape. It used to be an AND shape, and I'm going to turn it into an OR shape. The outputs used to be inverted, and now they're not going to be inverted. The inputs now need to get inverted, and that's the alternate logic gate representation. And on your final exam, you can have, the cheat sheet in front of you that shows that alternate logic gate representation. But really, you don't need that in order to do these questions quickly. You just have to change the shape and change the signs. So this is an example of why you would practically want to use an alternate logic gate. In this case, I wanted to activate the circuit with a low signal, so I have an active low coming out. I've made sure that I'm not inverted here or here, which is common best practice for making circuits. And I was able to switch around these two gates here in order to achieve that. And now this Z here goes low when X and Y are high, because you're at this part of the NAND gate truth table. But X and Y are only going to be high if A or B are low, or C or D are low. Therefore, Z is only going to be low if A or B are low and C or D are low. So that's how this alternate representation of the circuit performs.